Today we have the great honor to listen to Professor New Geoffrey Turok, who is the inaugural holder of the Higgs Chair of Theoretical Physics at the University of Edinburgh in Scotland, United Kingdom. New has received various awards and distinctions, including the 1992 James Clerk Maxwell Medal of the Institute of Physics from the United Kingdom, and the 2008 TED Prize for his work in mathematical physics and in establishing the African Institute for Mathematical Sciences, which he founded in South Africa in 2003. Since then, AIMS has grown into a network of various centers spanning the African continent and graduates over 300 students per year at master's level, and over 700 of its graduates have gone on to PhDs. In 2016, Neil was awarded the John Torrance State Medal for the Internal Leadership in Physics by the American Institute of Physics. In the same year, he was made an honorary fellow of the Institute of Physics in the United Kingdom. In 2018, Neil was named Officer of the Order of Canada in recognition of his substantial contributions as a scientist to the field of theoretical physics and cosmology. He served as director of the Perimeter Institute for Theoretical Physics in Canada from 2008 to 2019, in recognition of which he was awarded the title Director Emeritus of Perimeter. He also founded the Center for the Universe at a Perimeter Institute, a research center devoted to cosmology. New obtained his PhD in 1983 at the Imperial College in London. New is known worldwide for his relevant scientific contributions to mathematical physics and early universe physics, focusing on observational tests of fundamental physics and cosmology. Among several books, New authored The Universe Within, From Quantum to Cosmos, containing 5 lectures delivered across Canada and broadcast on Canada's national radio service, the CBC. For this book, he received Canada's top prize for popular science writing. But we are here today to listen to Professor Turok, so that I should not take you more of your attention with this introduction. Professor Turok, thank you again very much for having accepted our invitation, and from this moment on, the audience is yours. Thank you.
Sorry, someone is just calling me. I need to switch my phone off. Thank you so much, Louise, and thank you to everyone for joining me on this public holiday. I'm very grateful, and I sincerely hope I can be with you in Amazonia in the not too distant future. So what I'm going to tell you about today is an attempt to make sense of some remarkable discoveries in high-energy physics with the Large Hadron Collider, and in cosmology with all the observations we now have of the large-scale structure and nature of the universe. These findings were surprising to most theoretical physicists, and surprising in that they're simpler than we expected. The universe on very large and very small scales is stunningly simple and beautiful. All the complexity is on the scales in between. And the scales on which we live, our everyday scales, are probably the most complex in the universe. So I'm going to tell you about a somewhat new perspective on these problems, and hopefully some ideas about where theoretical physics is going in the future. As I mentioned, it's a public holiday in Brazil, and I would like to pay my respects to Zumbi dos Palmares. This is a remarkable day to have a day of Black consciousness. I am myself from South Africa, and in fact, my parents were both imprisoned for fighting against apartheid, and both ended up in parliament as members of parliament in the government under Nelson Mandela. So this is a cause which is very close to my heart. I was very fortunate, as Luis mentioned, to help start the African Institute for Mathematical Sciences. And I think going back into history, into the past, I'd like to recognize that our whole field, the whole field of mathematics and cosmology, comes from Africa. And so the oldest mathematical artifacts in the world are all in Africa. On the top left, you see the Blombos stone from the far south of South Africa, where there are the earliest known geometrical drawings of triangles and parallelograms in interesting shape, and that was 80,000 years ago. And then there are many other mathematical artifacts in Africa. On the top right is the Nabta Playa observatory, which, as far as we know, is the oldest astronomical observatory on Earth. And then, of course, the Great Pyramids and so on. So science originated in Africa, but was lost to the continent. And it's very important that it's brought back. And the African Institute for Mathematical Sciences, which I helped to start, now has 6 centers in Africa, in South Africa, Senegal, Ghana, Cameroon, and Rwanda. There are 2 centers in Rwanda. And as Luis said, it graduates about 350 students per year at master's level. And it's just beginning to grow a very large PhD program. And our goal is, by the end of this decade, a decade from now, we hope to be graduating 2,000 young scientists every year. We used to have the slogan that the next Einstein will be African. And I think that gave an impression to people of what we expected from young Africans in the future. We recently had a competition to revise our slogan because we didn't want necessarily an old white man to be the symbol of an African organization. And so we had a competition. In fact, the winning slogan was invented by our own students, a group in Cameroon. And they thought of this slogan that in Africa's youth, the future of science. And this is actually very plausible because, as you'll see demographically in this picture, Africa is the youngest continent in the world by far. The median age group is between 10 and 19. It's younger even than Brazil. You see on this map, the median age group is 30 to 39, but Africa, it's 10 to 19 in much of the continent. So these young people are the future. By 2050, something like 40% of the world's young people between 15 and 24 will be African. And so it's very plausible that most of the scientific and technical talent in the future will actually come from Africa. So I'm going to talk about cosmology and theoretical physics, the future of the field. But I really do enjoy interruptions and questions. So although you've been asked to save them for the end, I encourage you, especially if anything is unclear, to either send a chat message to Luis or unmute yourself and just ask. So we're in a strange situation today because at one level, we have been incredibly successful in understanding the universe. We now have a remarkably good fit. I would not call it a theory, but it is a fit to the large-scale universe. With just 5 numbers, we can describe all of the properties of the universe on large scales. 3 of these numbers are the energy content, the first being the cosmological constant or vacuum energy, the energy of empty space, and called rho lambda or lambda for the cosmological constant. So that is now measured with some precision. We then have dark matter, which another dark component in the universe, which which seems to behave just like non-relativistic particles would. So at some level, it's not that surprising that most of the particles in the universe do not interact with light. Their influence is felt through gravity. And so the dark matter seems to have an abundance of about 5 times that of baryons, ordinary atomic matter, in density. So dark matter density is about 5 times the density in ordinary matter. And finally, we have a certain number of baryons, or i.e. protons and neutrons, per photon. And that's roughly one nucleon one nucleon per billion photons. So those 3 numbers are sort of fundamental physics numbers, which we need to describe the energy content. And the goal of basic theory is of course, to explain those numbers. But that's, in a sense, all we have to explain, just 3 numbers. Then we have 2 numbers that describe the geometry of the universe on very large scales. So the geometry is stunningly simple. The universe has spatially flat geometry to good precision, just as Euclid imagined, flat 3-dimensional space, and small perturbations which are approximately scale invariant and take the form of Gaussian random noise. So they really could not be any simpler. And the perturbations are characterized by a variance. So if I write the variance of the gravitational potential squared, so this is just the Newtonian gravitational potential, you can still use the same variable in general relativity. It describes the perturbation away from flat space of the space-time metric. And its variance in the statistical ensemble at any point in space is a sum over Fourier modes. And we can write that as an integral d log k, so certain amount of power in each logarithmic interval in Fourier wave number, an amplitude, which is approximately 1 part in a billion. So that's the variance. And then a very small tilt, meaning that the amplitude of waves, of these Gaussian random waves on large scales, is very slightly larger than it is on small scales. So the scaling with k is approximately minus 0.04. So this looks just like a critical exponent. Namely, in condensed matter physics, one is very familiar with scale invariant phenomena, critical phenomena, typically at a second-order phase transition, in which the naive dimensional analysis gets changed by the effects of interactions. And so quantities acquire a scaling dimension. And because of that, the power spectrum and correlation functions scale with exponents which are slightly different than the naive classical ones. And we see this in cosmology. So there seems to be a critical exponent. It's very small. It's 0.04. But to first approximation, the perturbations we see are as simple as you can imagine. Just scale invariant Gaussian random noise with an amplitude of approximately a few parts in 10 to the minus 4. So a few parts in 10 to the minus 5, I should say. So many parameters that have been measured are so far consistent with 0. The spatial curvature is 1. The tensor perturbations, there could be long wavelength gravitational waves present in the universe. They don't seem to be there. Other kinds of perturbations are not there. Basically variations of the composition of the universe from place to place. Those variations are not there, and so on. So we live in an extremely simple universe. And this lambda CDM model is an incredibly successful fit. So the background plot shows the CMB anisotropy in the cosmic microwave background across the sky. And superposed on it, you see two graphs. One is the temperature power spectrum as a function of Legendre index or spherical harmonic number, the L in YLM. And the power is this oscillatory curve, which was predicted long before the measurements in the 1970s. And Jim Peebles essentially won the Nobel Prize for calculations of this, among many other things in cosmology. So this curve is exactly what was expected. The temperature fluctuation is about 1/3 of the gravitational potential fluctuation on large scales, and that's about 1 part in 100,000. So that's the flat plateau you see on the left. And then you see these famous acoustic peaks, which are really just the ringing of the hot plasma with sound waves. As it came out of the Big Bang, it was excited by the long wavelength perturbations, and they are now they oscillate as the universe develops in time, and these oscillations are reflected in these peaks. So the physics of these oscillations was well understood a long time ago. It's basically the physics of plasmas and gravitation. I was very fortunate to come into the field in the 90s, where nobody had calculated the polarization pattern of the microwave sky. In fact, some theorists claimed that this would be zero, that there would be no correlation between the polarization and the temperature. We calculated this from first principles using well-established equations, and we came up with this top curve. And amazingly, the modern data lies right on the curve, and there are actually no free parameters in that calculation at all. When you fit the cosmological parameters to the lower curve, the upper curve, the polarization, temperature, cross-correlation, becomes an absolute prediction, and it fits amazingly well. So experiences like this really led me to believe that the universe is both amazingly simple, and the physics is the physics we know. It works tremendously well on the largest observable scales. It's really very surprising. We have such an accurate description of the universe on vast scales. Now, inflation is the most popular theory of the origin of the universe. And I'm not going to dwell on it too much, just to say that this inflationary theory is becoming less and less plausible because the observations are going against it. So inflation's smoking gun signal is that there should be, if inflation happened, inflation is a burst of exponential expansion before the hot Big Bang. And this was proposed to explain why the universe is so smooth and flat on large scales. I'm going to explain to you a different explanation for those things in a moment. But so inflation has been a very popular idea. One of the reasons it's so popular is it predicted the fluctuations of the kind seen here. But it also predicts that there should be long wavelength gravitational waves. And these were claimed to be seen in 2015, I think it was. And that claimed signal turned out to be dust. And instead, what's happened is that the upper limit on gravitational waves has come down and down and down. So phi squared inflation, which is one of the very simplest models of inflation, is now convincingly ruled out. The current limit is here, the blue ellipse. So the upper bound on long wavelength gravitational waves and what's plotted here is the ratio of their contribution to the microwave anisotropy on large scales. The upper bound is now 3%, and in the next 4 years will fall to 0.3%. Yeah, here we are, by 2027. So as it falls, more and more models of inflation are being ruled out. By the end of this decade, the upper limit will be so tight that it will be very hard to motivate inflationary models anymore. I think inflation is becoming steadily less plausible. So this is very exciting because it means there's an opportunity now to lay a new foundation for cosmology, which hopefully will be even better than inflation. And that's what I'm going to try to explain today. Now, there's a similar story in particle physics. In spite of the predictions of many theorists, there have not been seen any deviations from the standard models up to 10 TeV at the Large Hadron Collider. So many theorists were expecting super partner particles, WIMPs, even small black holes might be created at the LHC. No deviations from the standard model have been seen, and it seems that nature has found a way of being consistent in a simpler manner than we theorists had anticipated. We see extreme simplicity on large scales, extreme simplicity on small scales. And the big question for me is, what is that simplicity telling us? Now, the traditional viewpoint, or let's say the dominant viewpoint in theoretical physics today, from string theorists and inflation theorists, is they would say that the universe is incredibly complex on microscopic scales, on subatomic scales, subnuclear scales, and incredibly complex on large scales because inflation typically results in a multiverse, a random, chaotic universe on large scales. And so the dominant paradigms would say this complexity will eventually be revealed by observations. Either at very small scales, we'll discover that space-time is really complicated and there's some six-dimensional compactification or whatever, or at large scales, we'll see some evidence of a chaotic multiverse. But currently, there's no evidence for either of those. And I think a much more exciting possibility is that maybe the universe really is very simple on very large and very small scales. And if so, it should be comprehensible using a simple and principled and predictive theory. And so I find this, maybe what we have ahead of us is an opportunity to complete the basic laws of physics with all the clues we currently have from cosmology and particle physics. Maybe there really isn't anything else. Our job is just to unify the laws we are already quite sure of. I want to say one other thing, which is that theoretical physicists, namely particle physicists and cosmologists, like me, are typically quite cavalier about statistical inference. Okay, it's not a subject which we are taught. It's not a subject which we take very seriously. And that is to our great peril, I believe. Because what we do as scientists, what we should do, is objectively look at natural phenomena, build theories, and test them. And we need criteria as to whether those theories work or do not work. Now, one of the sort of criteria we apply informally would be what's called Occam's razor, or the criterion of simplicity. If someone presents a simple and compelling idea and it fits the data, we think that's better. So we have some intuitive notion that simple theories are good. But in fact, there's a much stronger reason why one should go for simple theories. And this is explained very nicely in a book about information theory and inference by David Mackay, that if you do Bayesian statistical inference, it automatically embodies Occam's razor quantitatively. Namely, if I have a theory which has multiple possibilities and many parameters, like string theory compactification or like inflationary model building, then I make some observation, and it may be that some of those models fit the observations. Does that confirm the theory? No. The theory should be penalized by the Occam factor. The Occam factor is basically the ratio of the posterior accessible volume of parameter space and theory space to the prior accessible volume. In other words, you penalize a theory by all of its realizations which failed when you made the observation. Typically, so-called fundamental theorists don't do this. They feel free to make any number of models, and if most of them ruled out, they say, oh, well, we're starting again. You know, we'll make a new model which works. And I'm sorry, but that's not legitimate inference. So the reason they could get away with this for decades is there weren't any alternatives. And when there are no alternatives, you can say, oh, well, I have to do this, explore this multiverse, and I won't penalize myself because no one else has an alternative. So I'm going to propose an alternative which is much simpler and would not suffer from this problem of the Occam factor. So our question is, what is the minimal extension of known physics which is consistent with everything we know about particle physics and cosmology? And of course, it should be mathematically consistent as well. The deepest paradoxes and puzzles are our best clues. For example, the cosmological dark matter. That's a great clue, the Big Bang singularity, and so on. Now, let's talk about the dark matter. This perspective, which I'm explaining, which is that we should be looking for the simplest theories first, actually led us to a new theory of the dark matter, surprisingly, which had been overlooked, but is now the, I would say, the leading contender for the dark matter. So let me explain what the theory is, and then I will go through my talk, and at the end of it, I will explain what the theory predicts. So here's the standard model: quarks, leptons, the forces. And here is the theory with dark matter, okay? And you may not have noticed the change, it was so small, but you see the minimal standard model, so-called, has only left-handed neutrinos, but the most modest extension there is, and actually it's one we need to explain neutrino masses, has both right and left-handed neutrinos. So like all the other particles, the neutrinos in the extended model have both left and right-handed versions. And it turns out that just this extension of the standard model can explain the dark matter. Most plausibly, the right-handed tau neutrino would be the dark matter. And I'll explain at the end of the lecture how that works, and also what is the experimental signature. Because it turns out that in the next 3 or 4 years, this model that the right-handed tau neutrino is the dark matter will be tested to some precision. And if it's verified, this will strongly support the point of view I'm taking in this lecture, that really these laws on this slide may be everything there is in nature. Now, the physics we already know is quite unified, remarkably unified. I can write down a formal expression which includes all the known laws of physics: gravity, gauge fields, fermions, and the Higgs. And as far as we know, this is all we need to explain all of physics. The fact that we can write such a simple formula and that it's so unified and unique, these expressions are, given certain basic principles, these expressions are quite special and unique. There, of course, still big mysteries, ultraviolet divergences in gravity and the Big Bang singularity, and so on. But in principle, everything in nature is explained by what is on this slide. So we're starting from quite a advanced position in this field. Now, let us ask the following question. Why is the large-scale geometry of the universe so simple? Right? When we look out at the universe, it looks almost the same in all directions. It's isotropic, seems to be spatially homogeneous. There's no special spatial point in the universe, no center of the expansion. And it seems to be spatially flat, which we call kappa equals 0 in cosmology. Kappa is the curvature of spatial slices. Here's the space-time metric, minus dt squared, and a squared of t is the scale factor, Tp is the proper time. And so we have some symmetric space, three-dimensional symmetric space, which is expanding with the scale factor A of t. Now, to study this space-time and its causal structure, it's better to go to conformal time. You just change variables from dt from proper time to what is called conformal time. Conformal time, just in conformal time, the metric or line element takes this form of just a squared of t, a conformal factor, an overall scale, multiplied by a static metric. And so I will always use this conformal time picture of the universe. And then if you study a universe dominated by radiation at early times, as we believe our universe was, then the solution of the Einstein equations is that the scale factor is just linear in the conformal time. A matter-dominated universe has it quadratic in conformal time, and a lambda-dominated universe has a simple pole that the size of the universe blows up in a finite conformal time. And when t hits t star, we call that the future boundary, causal boundary of the universe. One of the surprising outcomes of our work is the realization that you can generalize this cosmology. Well, let me say the following. You see, from this point of view, it's really surprising how simple the Big Bang singularity is. The scale factor is vanishing as t goes to 0, but vanishing in an extremely simple way as a goes like t. In other words, it's analytic at t equals 0. And that means you can extrapolate it through t equals 0 to negative values of t. And when you then square a to find the metric, you still find a perfectly sensible space-time metric. So this was really a clue that in some sense, there's a sensible universe before the Big Bang, and it's simply the analytic continuation of the universe after the Bang. So that sort of started us on our journey. In fact, this is more general, that you can consider inhomogeneous and anisotropic spacetimes like the one we live in with perturbations. And as you go back to the Big Bang, the same is true, that even for perturbed universes, you can follow them through the Big Bang, and the maximal analytic extension is two-sided. By the way, in this respect, they're just like black holes. Black holes are also two-sided. The solutions of the Einstein equations describing black holes have two exteriors related to each other by analytic continuation. And so cosmology has the same phenomenon. And furthermore, the two sides of the universe, the before Big Bang and the after Big Bang, are exchanged by CPT. CPT is the most fundamental symmetry we know of in physics, charge conjugation, parity, and time reversal. And any Lorentz invariant theory consistent with basic quantum principles has CPT symmetry. And so basically, we came up with this hypothesis that the universe itself seems to be compatible with CPT symmetry. And that's our starting hypothesis, that in fact the universe respects CPT symmetry in spite of appearances. So the universe we're aware of is the universe after the Big Bang, where you come out in the radiation era, then there's the matter era, and finally the lambda-dominated era. But as I mentioned, you can extrapolate our universe back through the Big Bang singularity to the other side. That requires conformal symmetry, by the way, as I'll explain. And on the other side, you would find the CPT image of our universe, namely a universe expanding backwards in time relative to us and full of antimatter from our point of view. So this is a CPT symmetric universe. There's no difference between the left and the right universe. They're just CPT images of each other, and since the laws respect CPT, they are indistinguishable. The way we like to think about this is that what we're doing here is really imposing CPT symmetric boundary conditions on the universe at the Big Bang using the method of images. Namely, we impose some final state in the quantum theory, some initial state, which is exactly the mirror image of the final state under CPT. And then we find a semi-classical saddle point solution, namely an analytic solution of the field equations, which represents the classical background interpolating between the initial and the final state. And so that's our picture. So you shouldn't think of the universe before the Big Bang as a separate or different universe. It really is a mathematical device used to impose CPT symmetric boundary conditions at the Big Bang. Now, the reason for this analytic behavior of the scale factor, it's not a fluke. It is special to 4 dimensions. And the reason for it is that pure radiation has a traceless stress tensor. And this means that it is conformally symmetric. The conformal symmetry means that the physical laws governing the matter are invariant under conformal transformation. So there is, in a certain sense, no physical meaning to the size of the universe around the time of the Big Bang. The singularity can actually be blown up by a conformal transformation so that the universe has a finite size. And what you discover there is that the universe is analytic, smooth, and a sensible conformal 4-manifold. In fact, a class of them which are all equivalent. So this conformal symmetry is crucial, and it allows us to give a precise mathematical description of the Big Bang singularity. And so in a nutshell, we like to say that the Big Bang is a mirror. Just like when you solve Maxwell's equations in the presence of a mirror, you can either do it by imposing boundary conditions at the mirror and following the light waves as they bounce off the mirror, or you can make a mirror image of yourself behind the mirror and throw the mirror away and solve the Maxwell equations without a mirror at all, and you'll get the same result, just the method of images. So as I mentioned, this really does generalize to inhomogeneous universes as well. And just to remind you that in black holes solutions, this would be a typical diagram of a black hole solution, that there's an exterior universe, there are 2 exteriors and an interior of the black hole. We have the same phenomenon in cosmology. There are 2 sides to the Big Bang. And the reason for that is actually, here, all black hole and cosmological solutions are double-sided. And the reason is actually that both of them have nice Euclidean versions. That if you go into imaginary time, the black holes have perfectly regular solutions with no singularity at all in imaginary time. And when you come out of imaginary time, there are two ways to go in real time. You can go to the left or the right, and you basically get the two sides of the black hole. And in cosmology, we get the pre-Big Bang or the post-Big Bang universe. The virtue of these Euclidean solutions is they allow you to study thermodynamics. And so Stephen Hawking and collaborators developed the subject of black hole thermodynamics a long time ago. And recently we have extended this to cosmology. The goal is to construct a mathematical measure in the sense of a statistical measure or probabilistic measure on the set of spacetimes, on the set of cosmologies. Inflation was a sort of intuitive picture of how to make the universe flat and smooth. However, the measure it used was always implicit, not explicit. Nobody had a measure on inflationary spacetimes. They said, well, let's imagine the universe a little bit lumpy, and then when we blow it up with inflation, it'll become flatter. But they couldn't quantify that. Because we have a precise boundary condition at the Big Bang, which we are proposing, we're able to actually calculate the gravitational entropy for a spacetime. And that gives you a measure of how many states there are in any particular cosmology. So we follow the method of Hawking et al. We consider the theory, this would be a quantum amplitude going from initial to a final state in some time t. But if you analytically continue time to imaginary values, t is minus I beta, and then you identify initial and final states and sum over them, you get the partition function. And out of the partition function comes the entropy and the density of states. So we follow this calculation for gravity, and we show that the partition function for gravity is the exponential of the ordinary entropy, like the normal entropy of radiation, plus the gravitational entropy. And I won't go into the calculation of this, just to say that this is really unambiguous, crystal clear, follows straight from Einstein's theory of gravity, with this assumption that I can continue to imaginary time and thereby get the partition function. So we calculated the Hawking temperature and the gravitational entropy of cosmological spacetimes. This is just repeating. And this is what they look like. So we think about this in the complex t-plane, where t is the conformal time. And so along the real axis, we come out of the Big Bang with A going like t, and we head towards a singularity where A diverges, A hits a pole. So there's this pole, which is the future de Sitter boundary lying on the real t-axis. What we found is that we could solve the Friedmann equation for a realistic cosmology analytically. It turns out it's a Jacobi elliptic function. It's a doubly periodic function in the complex t-plane. So it has a very beautiful structure. And because the function is doubly periodic, it lives on a torus. The function lives on a torus in the complex t-plane. And so when you compute the path integral on these spacetimes, there is periodicity in imaginary time that's built in. And that period gives you the Hawking temperature. The partition function is topological invariant, namely if you compute if you compute it along if you compute the action along some complex path in this complex t-plane, it's periodic, and the answer depends only on the topological class of that contour. So you get remarkably clear, unambiguous results. They're mathematically unambiguous. There's no freedom in these results, and the gravitational entropy is what it is. So we were able to do these calculations for universes with any amount of radiation, matter, spatial curvature, and lambda, all the long wavelength properties of the universe, or large distance properties of the universe. So we calculated it for realistic cosmologies. We treated the inhomogeneities using perturbation theory, and we showed that this gravitational entropy, namely the log of the number of states, is greatest for homogeneous, isotropic, and spatially flat universes. So no need for inflation. The universe we see is a typical universe. Now we have a way of deciding what is typical and what isn't. We calculate its entropy. And secondly, it has a small positive cosmological constant. It turns out this thermodynamic picture only makes sense when the cosmological constant is positive. It cannot be defined. You cannot define a thermal ensemble at negative cosmological constant. So this is the thermodynamic explanation of the large-scale geometry of the cosmos. Inflation is not needed. There are still some puzzling aspects of this calculation. The entropy is a global property of a space-time. It's not the entropy of a configuration at a moment of time. It really is a non-equilibrium measure of the whole history of the universe. So it's a little bit unfamiliar, but it is very well defined. There was this rather nice picture in Quantum magazine when our preprint first came out, that if you imagine a set of universes given to you at random by some machine, then the universe we live in is the most probable, the one with the greatest number of states. What about the density fluctuations in the universe? Where did they come from? So this, I mentioned earlier, was a big success of inflation, is that it could actually give a mechanism for explaining the large-scale density fluctuations. Well, the form of these fluctuations is very simple. It's scale invariant Gaussian random noise to a good approximation. And what caused it? So we asked a very naive question. When we look at the sky, we see these fluctuations. What kind of quantum field would create those fluctuations directly, without any need for inflation or anything else? Just create them within a radiation-dominated hot Big Bang. And it turns out when you phrase the question that way, there's really only one answer. And I'll explain that in a moment. But before I get to it, let me just mention again that there's the most basic problem in reconciling quantum fields with gravity. There is an extremely basic problem which has been generally overlooked or hidden or ignored for decades and decades. The problem is that the vacuum energy is in quantum fields is divergent. And so on the right, we have a picture of the QCD vacuum, which gives you a picture of what's QCD fields are doing in the vacuum. And they're all fluctuating just because of the Heisenberg uncertainty principle. And if you add up the energy density in the vacuum fluctuations, it is infinite. Usually we renormalize this away, but this is very troubling because the basic question is, why does gravity not see this infinite energy in the vacuum? Now, there's an even worse problem in a way, because the divergences in quantum field theory spoil the local scale symmetry of Maxwell and massless Dirac fields. And we need this symmetry. This is conformal symmetry, and we need it to understand the Big Bang singularity. So it was discovered in the 70s that there are conformal anomalies in Maxwell fields, Dirac fields, the kinds of fields the Standard Model is built from, and those where the divergences, quantum field theory divergences, spoil the conformal symmetry. And it turns out these anomalies cannot be renormalized away. And so we can sweep the vacuum energy under the rug, but we can't sweep away the trace anomalies. They're called trace anomalies because they, according to them, the trace of the stress tensor is not zero, and that means that the theory is not conformal invariant. So it turns out that Standard Model fields contribute positively to both of these conformal anomalies, and so cancellations are impossible. With the usual fields we use, it is simply impossible to write down a theory which is quantum field theory, which is conformally invariant when coupled to gravity. So we thought about this, inspired by the observations, which, as I said, imply a particular kind of field, because this particular kind of field, which fits with the observations, is a four-derivative field, okay? So here's the action for a four-derivative field, which is locally scale invariant. And the reasoning is extremely simple. You see, when we look at the sky, we see scale invariant fluctuations. Scale invariant fluctuations can only come from a field that is dimensionless. A normal scalar field has dimension 1, a dimension and 2 derivatives in the action. A dimensionless scalar field has to have 4 derivatives so that the length dimensions cancel with the d4x. So in 4 space dimensions, to have a dimensionless field phi, you must have a 4 derivative action. 4 derivative actions have typically been written off by theorists because they are more complicated to deal with. They're harder to quantize. They give rise to negative norm states, as in gauge theory. Covariant quantization gives negative norm states, and you have to somehow project out these negative norm states. So these theories have been typically ignored. Few people have worked very hard on them, and we've recently developed them much more, motivated by the observations. What we find is that, as in a gauge theory, all the negative norm states can be removed, and one is left with a vacuum, with these dimension 0 fields fluctuating in the vacuum. In their vacuum, just by dimensions, they have a scale invariant correlation function. The phi is dimensionless, so the 2-point function has to be d3k over k cubed, meaning equal power in each log interval of k, just like the phi fluctuations in cosmology. So this is quite different than a dimension 1 scalar field, which has much more power in the UV. So these theories are very infrared, these dimension 0 scalars. So now we came back to the vacuum energy and the trace or conformal anomalies if we include these funny 4 derivative fields. So it turns out that the anomalies, the vacuum energy and the anomalies are proportional to sums of integers. How many dimension 1 scalars you have, how many chiral fermions you have, how many gauge bosons, and how many of these new dimension 0 scalars. And so they're just a sum of integers. We asked ourselves the simple question, is there any number of these new fields we could add which would cancel the vacuum energy and the conformal anomalies? And amazingly, the answer is yes, and the number is unique. And furthermore, the cancellation is only possible if there are precisely 3 generations of fermions in the standard model. So we have a rather compelling anomaly cancellation mechanism. Now, I have to tell you that cancelling all these anomalies implies that there cannot be a fundamental Higgs field. There are no fundamental dimension 1 scalars if this mechanism is to work. So naively, this is ruled out because we know there is a Higgs boson, and that's been measured at the LHC. But the Higgs boson, I remind you, is quite a puzzling thing because one essentially fine-tunes its mass to be much, much smaller than the Planck scale, and that's called the gauge hierarchy problem. If the Higgs boson is composite, and if it's made out of these new dimension 0 scalars, then in fact there is an opportunity to solve the gauge hierarchy problem. So we view this as an opportunity of a new way of explaining the Higgs boson, solving the gauge hierarchy problem. We're just starting to investigate that, and we'll see if it makes progress. But for the moment, let me assume that I'm in very high energies, ultraviolet energies, and there are no fundamental dimension 1 scalars. They're only chiral fermions, gauge bosons, and these dimension 0 scalars. So then it turns out that any 2 of these equations give that the number of fermions is 4 times the number of gauge bosons. For SU3 cross SU2 cross U1, the number of gauge bosons is 12. So we predict 48 fermions. And 48 fermions is precisely 3 generations, each with quarks, leptons, and each including a right-handed neutrino. That's pretty amazing that that cancellation works. It does not work for SU5 or SO10. Most grand unified theories fail, but the standard model works just fine. The cancellation implies there are 36 of these dimension 0 scalars. 36 is a big number. It's the dimension of the group SP8, which is in fact a remarkable group, sort of a mother group of twistor theory. But that again is early days. We're just beginning to understand what that means. So this is in principle a new route to unifying gravity with particle physics. I think of it like a new version of string theory, but you see string theory is itself based on conformal symmetry, but it's conformal symmetry in 2D on the string world sheet. This is conformal symmetry in 4D. It's a different mathematical structure, but it shares some features in common. So let me talk about the density perturbations. As I said, this was our motivation. We look at the sky, we see scale invariant density perturbations. Naively, those are the vacuum fluctuations of a dimension 0 field. Can we make this quantitative? So this is a little bit technical, but basically the answer is yes. We use the dimensions, we actually used a trick from string theory to cancel the anomaly in the trace of the stress tensor due to running couplings. Okay, and we just used a trick we imported a trick from 2D to 4D. The running couplings in the standard model violate scale symmetry. And we need that scale symmetry to be exact. And we want to use these dimension 0 fields to maintain that scale symmetry. So it turns out you can do that. And the way you do it is a copy of what you do in string theory. You couple the dimension 0 scalars to the trace of the standard model stress energy at finite temperature. And that's a perfectly calculable quantity. And when you do this, you find that these dimension 0 fields are feeding into the energy of the universe, of the plasma in the hot universe. And basically, they then enter into the Einstein equations, and they cause the scale factor of the universe to grow at a different rate in different places in space, because this dimension zero field is fluctuating from place to place. So we figured out how to transform, how to convert the fluctuations in dimension zero scalar fields into the curvature perturbation of the universe on large scales. And that's what we see in the cosmic microwave background. And all of these factors here are known standard model physics factors: the number of degrees of freedom, the coupling constants of the U1 hypercharge, SU2 weak, SU3. So these are all known quantities. Going through that calculation under some technical assumptions I don't have time to explain, but I'm happy to answer afterwards. We found that imposing conformal symmetry implies the following power spectrum. Namely, we got all these numbers. The C betas here are to do with the trace anomaly in the standard model at finite temperature. These are known coupling constants, number of degrees of freedom, wave number, and then this critical exponent, which we literally calculate as a critical exponent. Alpha 3 is the strong coupling constant extrapolated to the Planck scale. So we calculate this from first principles, microscopic physics. We then extrapolate it to observational scales just by completely naive extrapolation. And amazingly, what comes out is an amplitude which is a factor of 2 different than the Planck satellite measured amplitude. And this spectral index, or tilt, remember the scaling with K was NS minus 1. That gave the minus 0.04. This is the Planck measurement. This is our prediction. So we're saying is that the 0.04 is actually 7 times the strong coupling constant divided by pi, where alpha 3 is evaluated at the Planck scale. I remind you that the strong coupling constant runs with energy, and so using measurements at the LHC, you can extrapolate to the Planck scale, and that's the value we use to calculate the spectral tilt in the large-scale cosmological fluctuations. So remarkably, things work. This is an extremely predictive theory. There's no other theory I know of that predicts the numbers which are seen in this way, certainly not from the standard model. If it is verified, if more precise calculations and better measurements continue to verify this, continue to support this coincidence, then I think we'll have an extremely compelling explanation for the origin of the large-scale perturbations, a quantitative one, in which literally the early universe is a microscope, allowing us to see physics all the way to the Planck length. I told you I would explain the dark matter as being due to the right-handed neutrino. So let me end by explaining that. So first of all, let's count 16 to confirm the number I told you before. So in each generation of elementary particles, the up quark, there are 6 because there are 3 colors, and then there's left and right. There's 6 down, so that takes us up to 12. And then there are the electron has left and right, and the neutrinos left and right. And so altogether we get 16 chiral fermions in each generation. 12 plus 4 is 16, and 3 generations, that's the 48. Now, how do we, what we are claiming is that the heaviest right-handed neutrino is the dark matter. Why was this not proposed before? It's totally obvious when you think about it. The right-handed neutrinos have no gauge couplings. Okay, they're forbidden by anomaly cancellation, actually, chiral anomaly cancellation. And so they are neutral for all the gauge couplings. Only gravity sees them. Why did nobody propose that the right-handed neutrino is the dark matter? It is the obvious candidate. The reason is because for it to be the dark matter, it would need to be stable. If it's stable, it does not interact with the Higgs, as I'll explain, because otherwise it would decay into the Higgs. And if it doesn't interact with the Higgs, nobody knew how to calculate its abundance. You see, if it's not in thermal equilibrium with the plasma, how do you estimate its abundance? It would seem to be just an arbitrary initial condition. So people didn't like that, and so they assumed it is unstable and interacts with the plasma, and then you don't have to worry about its initial condition. So it's a strange reason to ignore the most obvious dark matter candidate, and I'll come back to how, in fact, it is a good dark matter candidate. If you consider a neutrino in this CPT symmetric universe, what you discover is that its field equation is regular at the bang. In other words, there's unambiguous propagation right across the maximal analytic extension of the space-time. Having done that, you can select in the quantum field theory the CPT symmetric vacuum state for the right-handed neutrinos. When you do that, you find that the CPT symmetric vacuum state actually has a finite density of particles coming out of the space-time in the future and in the past. That is because the space-time is time dependent, and so different vacua would appear to be full of particles from the other person's perspective. So, for example, there's an out vacuum, but the out vacuum is not the same as the CPT symmetric vacuum. So we pick the CPT symmetric vacuum because our principle is that the universe should be CPT symmetric, and we predict the number of right-handed neutrinos coming out. It turns out if one of them is stable, its density matches the dark matter density if its mass is 5 times 10 to the 8 GeV, which is completely reasonable. So we can easily fit the dark matter with one right-handed neutrino. But it's much better than that because we make a prediction as well. Now, this is our right-handed neutrino. If we want it to be stable, we do not want it to decay into Higgs and a left-handed neutrino. By the way, this same diagram is how you get neutrino masses for the light neutrinos. They mix with the heavy ones. That's the seesaw mechanism as they propagate, and this gives them a small mass. So, but the same diagram, you can see how the right-handed guy can decay. So to stop it decaying, we want to switch off that vertex. Turns out that's trivial. You can switch it off by imposing a Z2 symmetry. One of the 3 right-handed neutrinos, we insist that physics is invariant under nu right goes to minus nu right for one of them. It's a little bit ad hoc, but it's very simple. And it works, and it ensures it's stable. So it can be the dark matter. But that vertex is the same as the other vertex. And the other vertex is what allowed the left-handed neutrino to oscillate into the right-handed neutrino. So if you switch off this vertex, it turns out that so if I make one of the right-handed neutrinos stable, I end up making one of the left-handed neutrinos exactly massless. And that's the prediction, that the lightest neutrino is massless. This prediction is about to be tested using galaxy surveys. If what we know of the light neutrinos is there are 2 mass differences, or rather mass squared differences, between the lightest, next lightest, and the lightest, the next heaviest, and the heaviest. So we know the 2 mass differences from experiment, but we don't know the absolute scale. So we just predict that the lowest guy has to be on 0. there's either a normal hierarchy or inverse hierarchy. We predict that the lightest one is 0 in each case. This enables us to, from the known measurements, to predict the total sum of neutrino masses. And that is now what is being tested by galaxy surveys. This is the current data. It actually seems to favor a negative sum of neutrinos, but the error bars are huge. Our prediction is 0.06. And what we are predicting is that these curves, when the observations improve, will tighten into narrow peaks, a narrow peak around 0.06. If this happens, that will be very strong evidence that the lightest neutrino is massless. That will be strong evidence that one of the right-handed neutrinos is stable. And in that case, I think there's no question this would be the best candidate for the dark matter. There's no need to look any further. So to summarize, we have a thermodynamic explanation for the large-scale geometry of the universe. We do not need inflation. We've got a new way to cancel the standard models vacuum energy and trace anomalies. It predicts the large-scale density perturbations. It predicts 3 generations of fermions, each with a right-handed neutrino. It gives us a testable explanation for the dark matter. I haven't explained this in the talk, but it's also true that the same picture can explain the baryon asymmetry of the universe, why there's more matter than antimatter, through leptogenesis. These right-handed neutrinos violate lepton number, and it turns out this automatically gives you a mechanism to explain the matter-antimatter asymmetry. So this is very exciting. We think that all of those parameters of the lambda CDM model can be explained in this way, but this is clearly only just the beginning. It's a new start to cosmology, and much remains to be done. So thank you very much for listening, and I would welcome any questions.
Thank you, Professor Neil Turok. And before we continue, I'll ask for you to turn on your microphones for a huge round of applause for Professor Neil Turok. You see, now we have, I mean, in your previous webinar, we didn't have this possibility of making these clap hands and fireworks and everything. You see that, I mean, things have evolved a bit, right? Well, I mean, well, it's not the same as being here, but I'll keep my wish at one day to have you here. But let's move on then and see some questions that we have. So I will start by Professor Maurício Calvão from Federal University of Rio de Janeiro in Brazil. It is in Brazil, right? But it's about more than between 2,000 and 3,000 kilometers from where I am now. So anyway.
Okay, right.
Please, Maurício, turn on your microphone and make your question.
Okay, thank you. First of all, I would like to thank both you, Crispino, and of course, Professor Turok, for the excellent, very illuminating and intriguing and also predictive lecture. And I have some, perhaps lots of questions, but I will choose some 2 or 3. And first, I would like to make a comment on your proposal for the dimensionless scalar field, the extraction.
Thank you. Yes.
It involves a higher order, second order derivative of the scalar field, and so
right.
I guess you may have, or you must already have thought about it. It might give rise to more than second order equations of motion. Should that be a problem? Or?
Yes, thank you.
Unless it's a degenerate.
No, thank you. It gives rise to 4 derivative equations of motion. And these are usually argued to lead to instabilities So there is, oh, what is the name? There's a Ostrogradsky instability.
Ostrogradsky, yeah.
Right. So Ostrogradsky in, I think, 1820 showed that if your Lagrangian has more than two derivatives, then the Hamiltonian is inevitably unbounded below. Okay, so classically, this theory is very difficult in the sense that you can put arbitrary amounts of negative energy into these fields, and you worry that there will be a blow up, that I can, in a certain, yeah, that some field with positive energy, which couples to this negative energy field, can get bigger and bigger and more positive energy, while the negative energy field, runs away. So that is a worry that such theories are classically unstable. Now, 2 points about that. We're very used to dealing with a theory which has an unbounded below Hamiltonian. That's called the Dirac fermion. And Dirac famously resolved this problem of unboundedly negative energy by filling all the negative energy states with electrons, so that, and then using the Pauli exclusion principle to to prevent those states getting further occupied. That was for fermions. When you quantize this four derivative field theory, it turns out that there is essentially a choice. Either I accept negative energy states, or I keep all energies positive, all states have positive energy, at the price of some states having negative norms. Okay, so you can trade the problem of unbounded energy below for the problem of negative probabilities. Okay, so that may sound equally bad. However, we are quite used to dealing with states of negative norm in covariant quantization of gauge theories, right? So the vector potential has four components. The time component of the vector potential in Lorentz gauge creates states of negative norm. And what we do is we have gauge symmetry and we have constraints which eliminate all the negative norm states. So we end up working in a Hilbert space, which is positive definite, and that's the physical Hilbert space. So what we have recently shown is that with this four derivative theory, if we quantize in that way, so that all states have positive energy, and then we impose a projection onto a physical subspace, we can prove a no-ghost theorem to show that any state which is built from positive norm, any positive norm state, which will only propagate into a positive norm state. You can never propagate a positive norm state into a negative norm state. So we believe we have solved that problem, and that these interacting dimension zero scalars are actually very interesting quantum field theories. It turns out they're asymptotically free, and in many respects they're quite similar to gauge theories, but to non-abelian gauge theories. But you have to, but their quantization is certainly quite intricate. But yeah, thanks for the question.
Okay.
And I should say, so this recent work is not yet published, and other people are working on this kind of problem. These four derivative theories have become popular as a sort of model for four derivative gravity. And so Bob Holdham in Toronto and let me see, various other people have been working on them and discovering that they have rather interesting properties. So it seems to me, you see, the way I envisage what we're doing is we're actually discovering new ways. Oh, I should mention one other thing, if I may. if you ask for the influence of the Standard Model on the graviton propagator, so graviton, loop of Standard Model particles, graviton, this propagator has a number of bad properties. It has bad poles in the complex momentum plane, acausal poles. It turns out when you add these dimension zero scalars, they cancel the problems. And so the graviton propagator has all the right analyticity properties. It's related to the cancellation of conformal infinities. So essentially what we're trying to do is build a theory which has all the good properties of string theory, but only involves four-dimensional ingredients. And you see, in string theory, the world sheet coordinates of a string, if you ask what are they in terms of fields, they are dimension zero scalars. Because in 2 dimensions, the action is integral d2 sigma grad x squared. X is dimensionless. And so you can build vertex operators by exponentiating dimension zero fields in 2D. That's how string theory works. In 4D, you can exponentiate these dimension zero fields to get fields with non-trivial scaling dimension. And that's where I suspect the Higgs boson will come from.
Okay, thank you. Perhaps just to make it short, as my second question is related to the puzzles and paradoxes you listed, such as, of course, dark matter, dark energy.
Yes.
And I wonder and would like to have your opinion about the Hubble tension. Why didn't you
thank
list,
you.
and what's your opinion on the Hubble tension?
So, yeah,
A bit
so
off topic,
no, that's right. And I think both particle physics and cosmology continually throw up paradoxes and puzzles. They are, so far, for the last 4 decades, these puzzles have appeared and they have almost always gone away. They have gone away, actually. They have all gone away. So one shouldn't get too excited about a 3 sigma discrepancy. The astronomers I take the most seriously are relatively cautious about the data. Wendy Friedman, for example, continually cautions against taking the Hubble constant, the Hubble tension too seriously, because she says the errors involved in astronomical measurements are, just can't be compared to particle physics experiments. The cosmological measurements of H0 need to be taken seriously. That is coming from the Planck satellite, for example, because those are relatively clean and it's hard to imagine they're going to change much in the future. But the astronomical measurements could well change by a few percent, 5%, very easily. So I would say don't get too excited about the Hubble tension. Having said that, if it does become proven, it obviously is very, very significant, and it would require some change to the behavior of gravity on large scales in the universe. Again, a dimension zero scalar could do that, you see. I don't want to get into predicting it before I'm sure it's a real phenomenon, but and the dimension zero scalars, the simplest scenario is that they condense and form something like a Higgs field and just sit there in the vacuum and do nothing. But a dimension zero scalar, if you treat it naively, it actually does induce a long-range force, right? If I couple, so if you say my Lagrangian is grad squared phi squared, and then I couple phi to a source, as I would do in electrostatics, and treat phi as a sort of static field, it turns out that phi mediates a linear potential between objects. And so that really just does change large-scale dynamics. So it is not impossible that these dimension zero scalars really would alter the long wavelength behavior of gravity in the universe. And so I think that's unlikely, but at this stage of understanding it, it's a possibility.
Okay. Thank you very much.
Okay, thank you, Mauricio. So perhaps if you want in the end to make other questions, depending on how time goes. Well, I should not make any question as the chairman, let's say, of the session anyway. But given this alternative, I mean, this explanation to dark matter with the right-handed tau neutrino, right?
Right.
We have this things in, let's say, the things like the bullet cluster,
Right.
configuration for dark matter, and
Right.
how would you try to fit these things that these evidences that we already have in experimental, let's say, cosmology, astronomy, or whatever?
Right. So, yeah, great question. The answer is a little bit sad, which is that the right-handed neutrino would behave like extremely cold dark matter. That's all. Okay. It is created when the Hubble constant in the early universe is approximately equal to its mass. That's really when it's created. So you imagine a temperature of, 10 to the 9 GeV. You're essentially creating these particles out of the vacuum. They're created just due to the time dependence of the metric. And thereafter, any peculiar velocity they have redshifts away. So they really are static, cold particles. And later on, as matter clumps, they would clump just like cold dark matter. So they are a absolutely canonical cold dark matter candidate. They're much colder even than an axion. And so the best hope for detecting them, I think, and we've only thought a little bit about this, is simply the shot noise in their gravitational potential. So these particles are quite relatively heavy, 5 times 10 to the 8 GeV, and it means that literally as it travels through space, this would induce a gravitational potential, which would be time dependent. And so I have thought a little bit about whether you could somehow see the influence of clumps, gravitationally bound clumps of these cold dark matter particles, but it's extremely difficult. We just don't have. That would be the most obvious way, I think, to detect them, is to look for the gravitational effect of the literally very small clumps of these right-handed neutrinos which have formed gravitationally. But it's a very futuristic, gravitational detector, which would be able to see that. So it's tough. The answer is it's very tough to detect their effect other than through gravitational effects. So they would look exactly like cold dark matter in the bullet cluster or all the other tests of cold dark matter. And none of those tests have been able to really rule out completely cold dark matter. That's still the leading candidate explanation for all of the astrophysical effects of dark matter.
Okay, thank you very much. So let's move to the next question. It comes from Satish Kumar from Unirio, also in Rio de Janeiro. So please, Satish.
Thank you so much, Luis. Once again, you've done it again. Thank you, Neil. It's always very soothing to hear you. Not just for the physics part, like just to hear you is so pleasant.
Thank you.
So I have lots of questions because you don't get to talk to Neil Turok every day, but I have to control myself. I will ask maybe a couple of questions. No doubt, the universe is very simple, right? So we fit it with only 5 parameters. I was thinking 6,
right.
But you boil down to 5, okay?
Yes, Martin Rees wrote a
correct.
famous book called Just 6 Numbers. So yeah, the first thing is cosmologists always get numbers wrong. But more seriously, he used a number which is let me see, the optical depth of the universe. But this is not a fundamental number. This is a number due to, creation of stars and their radiation and reionizing the universe. So I don't count that number. It's not a fundamental physics. Now, I'm only counting the number of fundamental physics numbers, which are not, not explained in any other way. And yeah, there are only 5.
Fantastic. So maybe perhaps next time when you meet Sir Martin Rees, you should ask him to bring out the second edition with just only 5 numbers.
Yes,
right?
exactly. Exactly.
So now to play the devil's advocate, just
Sure.
for the sake of it, right? So
Sure.
is 5 number, is it simple enough? It's simple, but is it simple enough? Why am I asking this? Because apparently von Neumann critiqued Enrico Fermi, saying that I can fit an elephant with 4 parameters, and with 5 I can make its tail or
Trunk
trunk
wiggle,
right?
Wiggle,
So
yes.
is our elephant wiggling its trunk? Can we fit it
Yes.
with lesser than that?
No, we would like to. Obviously, we would like to, and we should try. I think this, the standard model is relatively complicated. Okay. Certainly, as compared to extensions, it is amazingly simple. If you compare the standard model to SO10 grand unified theory, the standard model is way simpler, okay, and doesn't predict magnetic monopoles and has many other advantages. If you compare the standard model to string theory, it's even more. It wins every day. But so standard model is relatively simple, but also puzzlingly complex. I mean, it has 20-something parameters when you include the neutrinos and neutrino mass matrix. It has many parameters. So you would like something simpler. One kind of perspective, I don't really have anything to offer on that, anything new, except perhaps this SP8. I'm excited about that. That is a new approach to unification, which connects with twistors. And I think probably the way to go is to try to unify space-time symmetries with internal symmetries. So there has been a no-go theorem for many years called the Coleman-Mandula theorem that said that the only allowed symmetries in physics were direct product of Poincare and internal compact symmetry group. I think what we're seeing with these dimension 0 scalars is a way of dealing with non-compact symmetries, which is I can't really explain this, but it comes along with them, where you are able to project out negative norm states and deal with negative energies through quantization. And that, I think, will enable new approaches to unifying space-time symmetries with internal symmetries. So I believe that up till now, the last 40 years, physicists took the easy option. They said, okay, we have Poincare symmetry, and then we have internal symmetries, and they don't talk to each other, right?
That's right, yes.
And then the internal ones, we just look at compact, simple Lie groups. But I think nature is more subtle than that. And nature, in unifying, gravity and space-time with gauge fields and so on, my suspicion is that it would do something more subtle. So that's why I'm excited about SP8. SP8 is a non-compact group, but it has a compact version, and it connects with twistors and Lorentz symmetry and conformal symmetry. So I think we just need to dig a bit deeper, and we may still find, we may find new routes to unification, which do not bring proton decay, magnetic monopoles, all of those disasters of grand unified theories.
Thank you for the answer. And also, you have lots of predictions, right? So these days, it's very hard for, I'm a theorist myself, like you. So it's hard for theorists to come up with receipts, right? So
Right.
It's very refreshing. Someone says these things, right? So it's very refreshing. So You have a dark matter candidate, a right-handed
Yes.
tau neutrino.
Yes.
Are you able to calculate the cosmological constant, for example? Because you have many anomaly cancellations, these kind of
Yes.
things. Does it bring
No,
down
that
the 10 to the 20 order to something finite?
right. So that's a great question, and indeed, it's what I've been spending the last few weeks thinking very intensively about. Um, the answer, you see, if you take this point of view, if you believe the measure on universes provided by gravitational entropy, okay, so it's a very unfamiliar thing. It's a way of counting states, which counts the states corresponding to a entire space-time. Okay, so and again, when we're doing this mirror method of images in cosmology, we're actually using a very fundamental property of quantum mechanics as opposed to classical, which was emphasized by Aharonov. So I'm very influenced by Yakir Aharonov, who is one of the leading exponents in quantum foundations, who has spent a lot of time thinking about what quantum mechanics means and how it should be implemented properly, et cetera, et cetera. The point he makes is that one fundamental difference between quantum mechanics and classical mechanics is that in classical mechanics, you can completely prescribe the system at one time, okay, and one time only. I can tell you the coordinates and the momenta at one time, and then I can't do anything else, right? Now in quantum mechanics, I can give you the wave function at one time, psi of x, and then I can give you the wave function at a different time, right? Psi of x and 0 and psi of x and t. And what I can do is compute the overlap of these two wave functions. I take my initial wave function, I evolve it to the final time, and I compute the overlap. Or I take the final wave function and evolve it back in time and compute the overlap with the initial wave function. So he calls this the two-time approach to quantum theory, that quantum theory gives us the freedom to completely specify the system at some initial time and at some final time. And in the context of cosmology, you see, this is particularly attractive in our setup because we identify these two times. So we prescribe the universe is in some state, if you like, long before the Big Bang. And then we say it must be in exactly the same state long after the Big Bang. And we identify those states, and then we sum over all of them. We trace over them. So this gives you a sort of unbiased quantum ensemble of universes. Now, it's a little bit teleological, right? Because you're prescribing the state in the far future. Yes. And so it is the opposite perspective of what people were thinking about with inflation. So with inflation, they imagine, you know, that the creator or something starts the universe in some highly dense, lumpy, random state, and then you run it forward, you know, classically. I think that is an extremely unlikely perspective to be true. Why would you start the universe classically kind of at the Planck time? That's precisely the time where you have no idea what space-time means. You know, you don't want to start the universe in a configuration where nothing makes any sense. Your picture of space-time doesn't make any sense. So I think this is a completely different perspective, whose danger is slightly teleological. You know, that why should we apparently see this arrow of time going forward when in fact, you know, the ensemble of universes is prescribed in our future. So that's the kind of question I think is very, very important to think about. Now, when you take that point of view, you say, what is lambda? What is the cosmological constant? I think there is a very attractive possibility, which is that the cosmological constant is a Lagrange multiplier for the 4 volume of space-time. Okay. If you think, how does it enter in the action? It's lambda times integral d4x root g. It's the 4 volume. It controls the 4 volume. And so now if you say, you see, if we have this ensemble of quantum universes, which are prescribed in the way I gave you, but lambda is somehow just a parameter controlling the 4 volume, you can ask yourself, what does the lambda really mean? And I think the point of view I've been exploring, you see, from this point of view, you don't calculate lambda in flat space-time. I mean, it's nothing to do with that. Lambda is really a global property of the 4-dimensional geometry of the universe. I think that's much more likely to be a correct perspective. And if you calculate lambda in that way, the idea I've been pursuing is the following. You see, it seems to be that gravitating systems have a finite dimensional Hilbert space. That's a very strange thing.
As opposed to quantum mechanics where it's infinite.
Exactly. So in quantum mechanics or quantum field theory, the dimension of the Hilbert space is infinite. You just have, you know, more and more highly excited states. If you put in arbitrary amounts of energy, you can have an arbitrary number of states. But it seems that in gravity that is not true. When you pump energy into gravity, you know, if you pump it in on small scales, you'll just make black holes, and they will recycle the energy into longer wavelength waves. So gravity seems to include its own ultraviolet cutoff. It seems to have a finite Hilbert space. Now, so what I've been exploring is the idea that maybe, so we calculate gravitational entropy semi-classically using the Einstein action, but maybe that calculation is really just telling us how the system, how to parameterize the system how to parameterize a system with a finite Hilbert space. So basically, I compute this gravitational entropy, and then identify that. Examine the configurations on the boundary of Hilbert space under the fundamental assumption that the total number of states is finite. So this is getting a little bit technical, but basically, if I formulate things that way, it's not surprising that lambda takes the value it does. Lambda is, has a controlling role in the formation of galaxies. We know that in cosmology. You know, there's this famous coincidence problem. Why is lambda dominating the universe now? Why is it dominating so soon after galaxies formed? And the reason is that, you know, lambda, I think a very attractive point of view is that there really is a finite dimensional Hilbert space. Lambda is somehow controlling the way in which we describe these geometries. And when we have a sort of good measure, we're able to do thermodynamics on these spacetimes. It won't be surprising at all that lambda takes a value such that it, you know, is controlling the number of galaxies in the universe. Sorry, that's a little bit of a vague answer. That's because I'm still
I think it's much more than what I was expecting.
I'm thinking very intensively about these problems, and I you know, just as Hawking made this leap of understanding where entropy of black holes comes from, right? Now, the leap mathematically is extremely simple. You look at the Schwarzschild metric or the Kerr metric, and you find that in imaginary time it's periodic. And you say, wow, a period in imaginary time means a temperature. And then how do I compute its entropy? I just compute its action. That's all he did, is compute the action of the Euclidean spacetime. And then the leap was to say, aha, that's the entropy of a black hole. That's counting the number of states of a black hole. So actually, we can do all that for cosmology too. All the same simple steps Hawking took, we can repeat, and they seem to work. The question is, how do you interpret this? Is it entanglement? Is it, you know, but I think if we believe it gives us the finite density of finite Hilbert space and tells us how many states there are in that Hilbert space, we then choose the lambda, you know, accordingly. You know, basically, you cannot do thermodynamics without some kind of constraint. If I say I've got a box full of particles, you know, what's the most likely configuration of the particles? Well, you have to tell me something. You have to tell me the energy in the particles. You have to tell me how many particles there are. You always put in constraints. And in cosmology, the challenge is, what kind of constraint can we use? We know that there's no such thing as energy in cosmology. I mean, the Hamiltonian of a general relativistic system is zero because it's time reparameterization invariant. So you can't use energy. The only thing you can legitimately constrain is the dimension of the Hilbert space. Okay.
I think that's the breakthrough, right? So that's the identifying that gravity makes the Hilbert space finite is a breakthrough.
Exactly, exactly. So now we have these kind of semi-classical tools to try to understand what does that mean and how do we use that. And so I think we have a glimpse at how to do it, but it's already clear that if you do it in any sensible way, the problem of the value of lambda, you know, is transformed. It's not something you just go and calculate in flat space-time as the vacuum fluctuations in a field. It's much more like lambda is a macroscopic thing, like a chemical potential, you know, or a temperature. It's some parameter which controls the volume of the universe.
Fantastic. Thank you so much, Neil. Thank you, Luis, once again.
Okay, thank you, Satish. Thank you, Neil. So let's move to the next question. So it comes now from the northeast side of Brazil, Federal University of Paraíba. So Albert Petrov. Albert, please go on with your question.
First, I am happy to listen to the seminar. I am very grateful to Professor Neil Turok for this excellent seminar. And I wanted to ask two questions, relatively small. First of all, if we consider very small distances, whether you try to implement Lorentz symmetry breaking, because if the distance is very small, we should take into account quantum fluctuation of the geometry. Therefore, it is natural to expect that we can have Lorentz symmetry breaking. What do you think about this possibility?
So, sorry, what kind of symmetry breaking?
Lorentz symmetry breaking.
I'm not a. Can you spell the word? I'm just not hearing it clearly.
Lorentz symmetry breaking.
Lorentz symmetry breaking.
Yeah.
Right. Yeah, very interesting. I mean, people are exploring all kinds of. So, all of my work is about treating space-time as classical, essentially. Even the calculation of gravitational entropy uses complexified space-time, but it's classical and it solves the classical Einstein equations. And when I study quantum fields in a given background, we don't include the fluctuations in the background. So everything I've described is very classical. The gravitational effects are completely classical. I've just been to a very interesting workshop on quantum gravity, which brought in Sweden, which brought together all the different approaches. So there was string theory, there were causal networks, causal sets theory, there was computer simulations of causal triangulations. So lots of people trying different approaches to study real quantum gravity. And that was very healthy, because I think the truth is that none of these approaches have proved satisfactory. Okay. String theory doesn't really describe quantum spacetime at all. In string theory, you have to put a background metric, and then you quantize a string, and you can do scattering of gravitons and things like that, but you're not really describing spacetime. I was quite impressed by the discussions of causal sets. It's a long way from a continuum theory. You know, they can't really get GR out of it, but they are making some sort of progress to understanding how maybe a continuum limit is possible. Some kind of smooth model is possible. But yeah, the short answer is I don't think we have a clue currently about the fundamental nature of space-time. I don't have any prejudice myself. It might be a continuum, it might be discrete. I don't have any strong feelings. If it is discrete, that sounds like it is more compatible with a finite dimensional Hilbert space, you know, if it's really some kind of spin network or whatever. And then indeed, it would be perfectly possible that it breaks Lorentz symmetry on short distances. So yeah, I don't have much to add other than I think it's a fascinating problem. And there has been surprisingly little progress from all these different approaches. So it's a very hard problem. I'm not blaming the practitioners. I'm just saying it's a really hard problem, very fundamental one. I would love to see analog models of gravity, which would have to be non-equilibrium systems with finite dimensional Hilbert spaces. And I don't really know of any good examples so far. There must be simple systems which could be used as a model for gravity, but I don't think we have them yet.
Well, another question is very small,
Sure.
very short. You have mentioned that the expansion of universe, dynamics of universe should be CPT symmetric. Does it mean that we can have contraction of universe at some stage?
In our picture, no. In our picture, there are two sides to the universe. From our perspective, the pre-bang universe was contracting, okay? But that's only from our perspective. From their perspective, we would be contracting, but the thermodynamic arrow of time in both cases points away from the Big Bang. So no, I think it seems that in the simplest description of the universe, from the point of view of somebody on one side of the Big Bang originated in a singularity and is heading to future infinity. You know, another way of describing this is to say, the universe is so simple, the evolution of the scale factor goes from a simple zero in the complex T-plane to a simple pole, and that's it, okay? So I think the universe we live in seems to be extremely simple and to include, you know, functional dependence of the very simplest type, from a simple zero to a simple pole, and that's it. Yeah, there's no room for more complex behaviors. So the short answer is no. I don't think the universe will recollapse.
Okay, so thank you, Albert, for your questions. Thank you, Professor Turok, for your answers. So let's move to, well, you know, we are going through 2 hours, okay? So I think we should, you know, you must be tired. I mean, and so let us then limitate for more 1 or 2 questions, okay? And then
that's fine. Yeah,
okay. Can we keep for this too then? Okay, so let me then move to PhD student here in Federal University of Pará, Gabriel Ribeiro. He has a question. So please, Gabriel, can you turn on your microphone and make your question, please?
Yeah, so first of all, thank you for your great talk, Professor Turok. And
Thank you.
regarding the scope of this framework, in which conformal symmetry seems to play such an important role, is there
Right.
any expectation to find an holographic correspondence like ADS-CFT?
Yeah, a great question. Um, I think the answer, well, it's a very deep question, and it relates to these dimension zero scalars. Okay, so the dimension zero scalars actually have a very long history. It goes back to Heisenberg in the 1950s. He investigated the confining potential as a possible mechanism for nuclear physics, in nuclear physics. But they also go back to a proposal of Dirac, which predates holography. Dirac noticed that the conformal group in 4 dimensions has a very peculiar representation. It's called a Dirac-Singleton representation. And it's because it's a non-compact group, it has an infinite dimensional representation. And it turns out that infinite dimensional representation contains every representation of the Lorentz group for a massless particle of arbitrary spin exactly once. So it contains a scalar, spin 1, spin 2, only integer spins, but they're all contained once. Okay, so it's a funny property of the representation theory of the conformal group. Then there were 2 mathematicians in the 70s, this again predates holography, who noticed that they were trying to find an explicit quantum field theory which would implement Dirac's peculiar representation of the conformal group. And they came up with these dimension zero scalars on anti-de Sitter space. And actually, as I understand it, this was the first holographic quantum field theory. The mathematicians were Flatto and Fronsdal. And they, all their work was about constructing an explicit representation, infinite dimensional representation of the conformal group using dimension zero scalars. And again, they concluded this was a consistent, consistent theory. So I think holography has in fact arisen from conformal symmetry and dimension zero scalars. And yeah, it's an intriguing correspondence. What I would say about ADS-CFT is that essentially it's a way of implementing the conformal group, but the space-time picture in ADS-CFT should not be taken seriously as a model for the world. It's merely a mathematical device to build an interesting, set of representations of the conformal group. And so if you, in a space-time sense, it's not interesting, it's the wrong universe. It's nothing like our universe. And by the way, I mean, I think a number of people have been trying to build realistic cosmologies with asymptotically ADS boundary conditions. And I think this is really crazy. And the papers they're writing are completely insane. They put, these are very clever people. I don't know why they're doing it, but they put a piece of de Sitter space-time inside an anti-de Sitter space-time and then claim they have a consistent cosmology. I think this is really, really nuts, and not nuts in a good way, nuts in a very bad way. So I think we have to figure out how to implement conformal symmetry in physically realistic spacetimes, which I think is your question.
Yes.
Do we have ideas how to do that? I think we're reaching for them. If there are such spacetimes, they will include singularities of the Big Bang type. Blowing up singularities of the Big Bang type using conformal mappings is a very good area of mathematics. And I think, you know, the people study conformal blow-ups of singularities. And it's a very interesting subject. And so I think, indeed, that should be the way that holography develops. And it needs to get out of anti-de Sitter space.
Yes, thank you very much, Professor.
Thank you.
Okay, thank you, Gabriel. Thank you, Neil, for your answer. So let's move to the last question then. So it comes from a researcher from University of Aveiro in Portugal, but at the present moment is in Belém because we're having this symposium. So Pedro Cunha. Pedro Cunha, please turn on your microphone and make your question, please.
Hi there. So thank you very much. So I'd like to thank you for your fascinating lecture.
Thank you.
I found it very interesting and also quite thought-provoking. In particular, I was fairly intrigued by this idea of a mirror universe emerging at the Big Bang. So I have actually two questions, but my first question is, would this mirror universe be an exact replica of our own universe? Or would you expect quantum fluctuations to kind of introduce small, subtle differences between both universes, given that they are causally disconnected? So, for example, can we imagine a scenario where in this mirror version of our universe, we would find kind of a mirrored version of ourselves having an identical seminar, or would kind of the history of the universe be completely different?
No, it's a great question, and one I've wondered about a lot. I think the answer is that this universe and that one, I mean, one answer is that the mirror universe is merely a mathematical device. Okay, that's the simplest answer. It's a device which allows you to define a path integral, right? So as I said, I think the path integral for gravity is a fascinating thing. It can be thought of formally, and it's quite tricky to implement properly. But if we think about a path integral for the universe with a future boundary condition on space-time, some 3-manifold, for example, in the future, and then we literally make a mirror image of that 3-manifold, and wherever there's a particle on that final 3-manifold, we put an antiparticle on the initial 3-manifold, and then we sum over all of that. That is an interesting object to think about. Now, then you want to understand, you know, what's going on in between these two boundaries of space-time. The first answer is a classical solution. You know, there will be a classical saddle point. And our finding is that for CPT symmetric boundary conditions, there's a unique analytic classical saddle. As long as you have radiation, conformally invariant radiation present, to make the Big Bang singularity regular, then there is a genuine saddle for arbitrary perturbed 3 geometry being the same in the initial and the final state. Now, then you want to compute the quantum state. Our prescription is it's CPT symmetric. This means that whatever happens in the post-Bang universe is absolutely entangled with what happens in the pre-Bang universe, right? So these are not distinct classical universes at all. They are highly entangled, but they are allowed to quantum fluctuate for sure. Just like when you do a path integral, all paths contribute, including paths which are not symmetric. So there will be contributions of 4 geometries which are not at all symmetrical, and they contribute to the path integral, and they will induce fluctuations in both sides of the universe, and any given fluctuation doesn't have to be CPT symmetric. So the ensemble is CPT symmetric, but the individual four geometries are not. And quite what that results in, I think, one needs to do calculations to see what that looks like. But no, I don't expect to find in general a copy of this seminar going on the other side of the universe. It will be something much more subtle, that there will be correlations and entanglement in the quantum state. But yeah, it would be interesting to look at examples, perhaps in sort of toy model universes with only a few degrees of freedom to see what is going on.
Thank you very much. I think I understand. So
Okay.
for my second question, which is very quick, so this model that you have discussed, does it provide an accurate prediction for the observed density ratio of dark matter to baryonic matter?
Yes, it does. The prediction is absolutely precise. Unfortunately, there's one free parameter, okay, which is the mass of the right-handed neutrino. That's a free parameter, and we just fit that one free parameter to the observed density of the dark matter. And when we fit it, we infer that the right-handed neutrino, the stable right-handed neutrino, has a mass of 5 × 10⁸ GeV.
Okay. I recall that comment. Okay, I understand now.
Exactly.
Okay.
So it's just a fit. We can't claim any great success. We had one free parameter. We fitted one number. Unfortunately, further verification requires more observed numbers. There is something I didn't talk about in much detail, but you can ask, are there other predictions of this model where one of the right-handed neutrinos is stable? For example, there is a process called neutrino-less double beta decay. That's a very rare process which occurs in a theory with Majorana masses for the neutrinos. It violates lepton number. But the processes involved violate lepton number, and that is being looked for in nuclear physics experiments. Unfortunately, again, our prediction is that the rate of neutrino-less double beta decay should be its minimum, okay? Given the parameter space of a model with right-handed neutrinos, we predict the minimal possible rate. And this process has never been seen. It's hoped, optimistically, it may be seen in the next decade. With the predicted rate we give, it will take several decades to see the process. But if it is seen at exactly the rate we predict, which is the minimum rate, that would again confirm the idea that only 2 right-handed neutrinos couple to the other standard model particles. One of them is absolutely stable, doesn't couple to the standard model, only couples to gravity. So yeah, there are ways of confirming this, but they're experimentally very difficult. The other way, as I mentioned, would be to see the clumps of right-handed neutrinos created gravitationally and to literally measure their effect in gravitational detectors. People are building very small detectors now, very sensitive gravitational wave detectors. And one can imagine in the future such detectors will be put into space and they will literally be looking for lumps of dark matter particles flying through or through the detector, and then you would look for their signals gravitationally. But yeah, these are very, very difficult experiments for the future.
I can imagine. Thank you very much.
Thank you.
Thank you, Pedro. Thank you, Neil, for not only having gifted us with excellent science, but also with this excellent live examples, and particularly related also with this black awareness or black consciousness. And it was an splendid coincidence. We didn't fit it from the beginning. But I'm very, very grateful for you. And I will ask you before we finish for a great round of applause for everybody that is here in this audience.
Thank you.